Uh, Hello and welcome to today's problem. Yeah, given the root of a binary tree, figure out if it's a valid binary search tree. Okay, so
Yes, sir.
let me just take a look at the definition. It's valid if the left subtree of a node contains only nodes with keys less than the node's key, and then vice versa. The right subtree of a node can only contain nodes with keys greater than the node's key, and all of
Yep.
those subtrees must have to be binary search. Okay. Um, okay, let's take a look at the example one over here. We have two, 1, and 3. This one is a valid binary search tree because everything on the left is less than, everything on the right is greater. Um, so yeah, and then for this one, 5, 1, 4, 3, 6, it's false because if you take a look here, 4 is less than 5, yet it's on the right side. So we want to return there. Okay. Um, so there, one approach of doing this would be using in order traversal. I'm assuming. Just I'm thinking of in order traversal because you have to try to figure out what the left node element is and what the right node element is.
hmm
So I guess one way of doing this would be, let's say like we start off at number 5. The first thing we want to do is we want to check whether or not the left one is less than 5, which it is. From there, we have to determine whether or not one is also a valid binary search tree, whether or not it fits the definition. So I guess what we can do then is check to see, um, is the left like less than. There's nothing at the left, so therefore it must automatically be true. And from there, we can go ahead and check the right. Is it greater than? Nothing, so it's true. So this is valid, and then it'll move on to it'll just move on where this is valid, and then that's when 5 begins the right. So we want to check the left, and we want to check the right. So
hmm
let me just write up like a quick in order traversal template over here. So we have, let's say like okay. So first we'll have like find is valid search tree. I'm assuming okay. You're given the root, and from there you want to do in order traversal, um, and you're given the elements uh, node. So in order traversal is first you call itself in order traversal on the left. Yeah, and then in order traversal, you call that on the right, and then at the very
hmm
center, you're gonna want to perform some sort of action. So in this case, what we want to do is we want to figure out what the like whether or not it's the left is less than and the right is greater than. Oh, also before
hmm
we do this, we should probably call it on the head first. So we can do return in order traversal on the roots, and we're gonna want to check this as an edge case to see whether or not the root actually exists. And if it doesn't exist, we'll assume it's a binary search tree because it fulfills the criteria. Is that
hmm
yeah, okay. uh so if not root, then we want to return true. Okay, so
Yep.
so with this kind of like criteria in mind, we can first check to see whether or not uh node if node um node dot val is less, oh, if like the value on the one on the left is left dot val is less than, and if node dot right dot val is greater than or equal to, um oh, actually wait, that doesn't make sense. If it's greater than the current val. So that's what we need to figure out. If this criteria is valid, then we're going to want to return true. Um and everything on the left also has to match this criteria also, which is why we hmm, this is why we also have to, oh yeah, we have to include in order to oh, actually let's copy paste this. um we can return this, return in order traversal to the left, and in order traversal no dot right. Okay, wait. So actually, wait. Yeah, let me just walk through my thought process again. So we're given um we have to do an inner traversal. You want to check to see whether or not the any like the left is also a valid binary search tree. So you want to call it on the left, and you also want to do the same for the right. Um, if both of these checks work, if the node on the left is less than and the node on the right, that's when you want to return true. And also we need to have some sort of case, where there's nothing. If there is no node on the left, if okay, if not node dot left, we want to be able to basically just return okay. Okay, so basically we only want to actually so we only want to do an inner traversal on the left if it exists. Otherwise, we just want to return true. So let's actually do that instead. Wait, indentation's off a little bit. Okay. Return true, and then also same thing for the rights. If not, no dot rights. Want to return true. Else, you want to call in order traversal no dot right. Let's actually store the results of this in a variable instead. So we'll have like is left valid. Let's have that set to false as default. False, and then want to turn true, and then is left valid. We'll put the values in this variable instead. So we have if left valid in order traversal, and then same thing for here. We'll have is right valid equals true. So the logic with what I'm doing here is that I want to basically check to see if the left is valid, check the right is valid, and then if both of those are true and the current one is valid, that's when I actually want to be returning true for our final value. So actually I'll do it over here. So at the very end of this, you want to check if is left valid and is right valid, and okay. Okay. Oh yeah, we need to do it with the current value. Know that value, current that right. Then that's when you wanna okay, return this. Okay. Sorry. And is right valid and is left valid. So if the left one is valid and the right one is valid, and the one on the left is less than and the one on the right is greater than, then that's when you want to return true. And since we call this on the root, we can just run through this example again with the code I've written. You first call in order traversal on 5, and from there you want to check if the left is valid. First of all, like the left exists, so we call in order traversal on the left. Without a 1 value, we check to see if the left is valid. It's set to true. We check to see if the right is valid. That's also true because there's nothing there. So that's fulfilled. That's fulfilled. Ooh, okay. Oops. Is greater than no dot val. Since these values don't exist over here, we have to figure out a way to figure out a way to check for that. Let's see.
Right. So just to be clear, the idea is that on every node of the tree, so like you would recursively traverse down to every node of the tree and check to make sure that the left value is smaller than the right value, right?
Yeah. Well,
Okay.
so wait, the value is smaller than like the current value.
Right. And then the right value is also bigger than the current value, right?
Yeah.
So I think could we try considering the case of this tree? So let me draw out a tree, and then can you tell me if it looks like a legit tree or not?
Okay.
So let's say I have five, um, and yeah. So I'm just gonna start by copying the tree you have up top. Okay.
Oh, hmm. Oh, right. I was just thinking of that. So
Yeah.
you
So
have to check for like the parent as well, right?
right. So here, if you look at this, then it's true that like this would return true. On the left, it doesn't exist, which is fine. On the right, it's bigger, which is fine. Here, it would also return like let's say this was like that. Here,
Mm-hmm.
it would be fine. Here, it would also be fine. These would also be fine.
Mm-hmm.
But this is not a valid binary search tree because the seven would have never made it past the five.
Yeah. Hmm. Okay. Uh. Okay. So let me think about this. We're at the number 7, right? And we need to be able to compare it with 1, but we also need to be able to compare it with 5. So I guess that's where it gets a little bit trickier. Hmm.
Mhm.
So the relationship with 7 and 5 is its parents, um, its parents' parent to the right. And like, okay, let's say we have like a situation like this where we want to check the one previous to it also. Like 3, that doesn't work because it's greater than it's greater than 5. Whew. Huh.
So like I said, the seven would have instead of thinking of it in terms of like five is the grandparent of seven, and like trying instead of trying to think of like the relationship between seven and five,
Mhm.
just think about like I said that seven should have never made it past five, right?
Yeah.
So, um, like in the perspective of seven, on its like from the perspective of seven on its way down, what could have not happened?
Hmm. On its way down, it shouldn't have gone to the left when you're comparing like 5 and 7. It should have gone to the
Right,
right. Yeah.
right. Um, and then like you can imagine like I might have constructed like another example to prove my point here.
Uh-huh.
And if the number that's problematic was on the right side of the tree, uh, like in that example, like it would be fair for me to say
It
like
should have
let's
gone
say
to the left.
negative.
Like the other example is
Right,
like
right.
3, right? Okay, yeah, that makes sense.
Yeah. So like if I said like yeah, three, yeah, three should have gone to the like should have never made it past five either, right?
Mhm.
So can we put that in a little bit more formal terms? So like seven should have never made it past five
Uh-huh.
because five is smaller. Three should have
Uh-huh.
never made it past five because three is bigger, right?
Mhm.
So um, yeah, is there a way for us to kind of like as we traverse down, as your function traverses down the tree to inspect each node,
Hmm.
can the function kind of like keep in mind what couldn't have happened to the nodes at that point?
So we could okay, so we'd have to have some sort of data structure which basically keeps track of all the parents, right? Uh hmm. Okay. Uh
So what are we keeping track of? Let's say like from five, right?
yeah.
Let's say I'm done inspecting five, and then I go to inspect one, right?
Yeah. You want to
What
make
do
sure that like everything is less than 5, right?
yeah, that's right.
So then you'd want to maybe you could have like a variable that like checks to see like the greatest it can be. So like the maximum.
Okay.
And then
Um,
you have that, and then you also like a okay, yeah, wait, what were you going to say?
Yeah. Um, so like when I'm done inspecting five, and let's say the function moves on to one,
Hmm.
then the function needs to know that like one needs to be smaller than five, right? Whatever the function inspects from here on out
Hmm.
needs to be smaller than five, right?
Right.
And then let's say it's let's say instead of going for one after inspecting five, it went for six, right?
Uh-huh.
Then the function knows that anything that I find here needs to be bigger than five, right?
Hmm. Mm.
But you can imagine the needs to be smaller than x needs to be bigger than x changes as you go down the tree.
Yeah. So, um, basically, like you'd have like two variables, one to check what needs to be greater than, and one where it checks to be where it's like a less than, and you need to check
Okay.
whether or not like the current value matches those constraints before like you continue traversing downward. So,
Okay.
so like in this situation, we'd have okay, so we return lower left of val like this and this and this. We also okay. We wanna hmm we wanna okay basically to do check okay we want to have two values. We'd want like the maximum. Shoot, okay, let me think. Oh, like
Also, just fair warning, I realize I might have to head out for a short amount of time in not too long.
okay, okay, yeah.
Yeah, but
uh,
we'll cross that bridge when we get there. Like if that happens, I'll dip, and then if it's not too late, I'll recontinue if that's okay.
okay, sounds good.
Yeah.
uh all right, so okay, so we're given like the max. Okay, so like we need to with this one we have to try to figure out like a way to keep the keep track of like what the maximum can be at the given one. So would it be correct to say that we like utilize like a tuple and we keep track like actually wait, no, that wouldn't make sense because that would be changing the structure of the tree itself. Okay, what if hmm, okay, what if we create an array that keeps track of what's already been traversed through,
Okay.
and then from there we keep like adding onto it until like you finish like that specific side of the tree, whereupon like you reset it again. Actually, yeah. Mm, okay. Am I on the right track with having like those checks in place with like checking to see like the minimum amount and like the maximum amount?
Yeah, yeah, that's exactly right. But you wouldn't do it through an array.
Okay. So another suggestion could just to be have just have two like variables. Let's say like min amounts, and then you have like a max amount over here. So
Okay.
minimum amount is going to be like um uh like I get like maximum like shoot, I forgot what the Python thing is. It's like negative like inf or whatever, right? Or
Yeah, it's cast like in a float constructor, put in a string that straight up says inf.
oh, okay, okay.
Yeah,
So
that'll return infinity for you.
wait, a float constructor. Oh.
Like do float brackets and then a string that says inf.
Oh, okay, okay, okay.
Yeah, that casts the string into a float.
Mm. So the minimum amount is that, and the maximum amount is floats like negative inf, right? Or okay, so we have like the minimum and maximum over here, and then given that as you traverse through, you want to keep restraining it one by one by one. So um, okay, we're at five. We're at five right now, and from there we want to we just start to like go for like the left value. At this point, we know everything on the left has to be um what is it? Oh, it has to be less than 5. So at this point, we know that the maximum amount, we want to set the max amount and we want to set that to be the current value. So node.val before performing like is left valid. After you do that, you want to set the max amount, reset it back to like the like just set it to its default value again, or like the negative int value. Um, Likewise, for is write valid, you want to check like the min amount. Um, you want that to be equal to the node
Okay.
dot.
Wait one sec. Sorry, I gotta be right back. Sorry about the wait. I had to go fight some North Koreans, but they're dead now.
Yeah, he's was like a victory from the ashes, just like his completion of the League Code hard.
Yeah, yeah. Anyways,
Uh,
we can keep going.
okay, so back where we left off. Oh yeah, okay. So okay, right. So I wanna put the minimum amount as node.val. Uh, you do max amount floats and make that to infinity again to have it as a like a little reset. And then okay, so basically my explanation with this is we keep like the minimum and maximum amounts set it to like the lowest or highest value possible. You then check to see whether like you just then set the maximum amount to be that amount, and then you keep doing the method until it's completed. Oh, okay, wait. Found an issue with it. Um, Actually, wait, no. Let's see. Okay, let me just run through it with an example. We start off at 5. Go ahead and check to see like what its left is. The left exists, so then it sets the maximum amount to 5, and then it calls inner traverse on the left. It's valid. It's 1. So at that point, yep, that's good. And then at the very end, what it does is return that. Okay. Um, okay. To do it with the example that you said before, um, we have so we have 5. Check the left. It's 1. We know the maximum right now is 5. Um, we then check to see. Oh, right. We need to have somewhere to, um, basically like see whether or not it's less than or greater than the maximum amount. So we do, uh, and no.val is greater than the max amount, and or sorry, less than the maximum amount, and no.val is less than the or greater than the minimum amount. If all of that criteria is matched for, let's say, like 1, it's greater than the maximum. Wait, yeah, it's greater. It's less than the maximum, which is 5, and it's less. It's greater than the minimum, which is when it's negative infinity. Therefore, it's valid and returns valid, and then keeps moving onward, and it'll and then we start off with 1 again. So now we know that 1 is valid. We check to see it resets it again. The maximum amount is what is it? Negative infinity afterwards. So then like the cycle can basically continue repeating. Okay.
Right.
Yeah.
Yeah, that's the solution. You got it.
I got it.
Yeah,
Hey,
yeah.
that's hype. That's hype.
Um, yeah, that is pretty hype. It's like it's a pretty tough question. Just thinking back to when Gregor showed it to me, I don't know if I would have gotten it if he didn't show it to me.
Oh
Um,
yeah.
yeah, so that's good work.
Yeah.
That's fire, man.
No, you basically told me the minute the max bit, but like, yeah.
No, no. I mean, well, you told me the other part for the other question.
Uh. Oh. Okay.
Anyways,
Yeah.
yeah, so good work, man.
Should I go ahead and try running it? Let's see. It's probably a lot more errors, but we'll see.
You could.
Okay. Man. Oh. Yeah. Root of a binary tree. Or. Huh. I vaguely remember doing this. Like this is like a non-foreign concept. This is how they taught it back in 110.
I think so. Yeah, yeah.
Oh.
Except it was in like rackets.
Oh yeah, that makes sense. Glad I never have to do that again. uh. Okay, let me quickly, if not redo that. Otherwise. Do that.
Or
Oh yeah.
I think what does it run?
Wait. I'm just trying it. Hold up. Give me a second.
Okay, okay.
Wait, what were you gonna say though?
I was gonna say, it might be a good idea for me to provide feedback while, like provide feedback first, and
Oh,
then we can modify the code to run if you want to try it.
okay, okay, sure, sure. Yeah.
So, um, let's see. So, in your code, something I noticed is, um, you do a lot of forward checking. So what I mean is like before you make the recursive call, you
Mm,
check to make sure if the left or like left node exists. You check to make sure if the right node exists, and then you
mm,
you do stuff based on that, right?
yeah.
So the thing is, you don't need to because at the top you've written if not root return true. So what you can do is you can just let the recursive call happen, and then like in that iteration, it'll catch the fact that
Oh,
not root.
I see. So like I can modify this code instead of like doing all this like kind of like crazy stuff. You can just do if
Right.
not root at the top, like here, and then you could do like return true, and then
Yeah.
from here. Oh, okay, okay, that makes sense.
One sec.
Okay. Yo, we're gonna get killed by the North Koreans again. Okay. Mm. Okay, so we do that. Uh, yeah, I gotta pull this down a little bit. Pull that out. Looks valid. Then you call that. Turn that before going ahead and returning this in order to traversal. Okay, let's have a go on. Go ahead and run that. Okay, none type. Uh, oh, whoops. Hmm. None type has no attribute val. So you want to check for that. Oh. Hmm.
Hello.
Hello, hello, hello.
Hey, sorry, man.
Oh, no, it's all good. It's all good. Uh,
Okay, we can get back to it.
okay, okay. Hold on. Let me just modify this real quick. Okay. So, okay. So this is what I have right now. Um, you have like the basically I just like did what you said. If not node, then you return true. The problem is it's having an exception because like a null pointer exception
Mhm.
at like line 75. Cause what is it like? No, that left that file might not exist at like that given point, or like that like that's what I
Right.
think. Yeah. So
I can go ahead and write up the actually no, I think it's better if we write it out together.
okay, okay.
Um I think so first you probably want to get rid of is left valid is right valid because that's from like old stuff, right?
Where is it? Oh
Like we
yeah.
don't use is left valid is right valid anymore.
Oh yeah, yeah. Right,
So
right.
Yeah, you can just delete every line that contains a mention of is left valid or is right valid.
Yeah. Yeah. So like something like this, for example, and then do you want to check to see like that, right?
Yeah, and then you might also want to. I think it might be cleaner actually if like the thing is, um, right now we have global values for min amount and max amount, right?
Right.
So
We want to localize it.
um, like or no, rather like um, in a sense, every recursive call kind of points to the same like variables, which is a little bit confusing because every node has a different min amount and max amount to abide by, right?
Yeah.
So if every node has their own min amount and max amount to abide by, wouldn't it make more sense for them to be function arguments?
Oh, I
So
see. I see.
in order traversal, comma min amount, comma max amount, like that.
Yeah.
And then on your first call, you pass in float inf, float negative inf.
Right. Right. That makes sense. So then you do like a return in order traversal, and then you have the root. Then you have the or yeah, float inf float negative inf. Hmm.
Yeah,
Okay. Okay. That makes sense. Yeah. And then from there, the minimum, the maximum. Um. Okay. Max amount equals that, and then instead of like doing this, we can just pass in no dot val, and then like whoop, that's the maximum amount. Yeah. And then the minimum amount like that.
right, exactly. Yeah, because like when you turn left, right?
Yeah.
Like the when you turn left, whatever's on the left needs to be smaller than the current value.
Yeah.
Or in other words, the max value, the max amount updates, but the minimum stays the same, right?
Yeah. Um. Right. So okay, then we do this. So we're
Okay,
calling the left
so
and the right. Then we do it the math there, and
right.
then
So you do you want to try renaming this function to like validate instead of in order traversal?
oh, okay, yeah,
Because it actually doesn't matter whether it's in order or like post order or whatever,
yeah. This
because
to be post order. Yeah.
it doesn't matter. Because uh like all you need to do is make sure that like all you need to do is inspect each node and you get the minimum and maximum values via the path that you're taking. So
Mm-hmm.
it doesn't matter like in what order you're inspecting nodes, if that
Mm-hmm.
makes sense.
Yeah.
Yeah. Um so validate is going to return a boolean, right? To like let you know whether it's like true or not, whether that node
Oh,
is valid or not.
right. That makes sense. So we just call that validate method on here instead of doing that. Um.
Yeah, but actually I think a cleaner way to do that, if you want to put it back real
Okay.
quick.
Yeah.
So something I like to do when we return the logical combination of multiple booleans
Mm-hmm.
is it gets really messy if you put like the logical stuff like on the return statement.
Right.
So it's better if you do like is like left valid equals and then like right valid
Yeah.
equals and then you do cur valid
Uh huh.
equals and then you do left valid and right valid and cur valid.
Oh. Hmm. And then we have basically you
Yeah,
check
like
to
that.
see.
That just looks cleaner.
Hmm. Basically like node, or this one has to be greater than the left. And okay, that makes sense. Yeah.
Is it node.val.left though?
Oh, what the? What am I doing? Okay.
No, no, no. I mean like is this what you should be comparing it to? Like if
Oh,
you're checking whether the current node is valid, um, because this is our old method, right? Like this is our old method of just checking to make sure that the left one is smaller and the right one is bigger.
oh,
But we,
oh, right. If it's like if it's greater than the min amount, right?
yeah, yeah.
And then
or like greater than equal, or greater or equal technically.
Okay.
Yeah, not just greater and lesser.
Wait. Wait. Actually, wait. Why would it be greater or equal? Oh, okay. Wait. No. Wait. That makes sense. That makes sense. I think.
Yeah, because I'm pretty sure it's illegal for there to be same like identical nodes in a binary search tree, right?
I think so. Yeah. Yeah. I just kind of confused because of the definition earlier said it has to be less or greater than, but I think like the formal definition for it is that okay.
Yeah. And then also here, do you see where my cursor is?
Yep.
There should also be like a equal there because it's greater than or equal to. Same thing for the less than. Yeah.
Oh, okay, that makes sense. And yeah, that works because the minimum amount, if not no, then just return true. Okay. Wait. I just gotta think about that again. So you no longer have to check to see like whether or not like let's say like for this example, line
hmm
25, you no longer have to check to see like whether or not it's one, like one is less than because it does that for you, right? The- right. Okay, that makes sense.
You mean like you no longer have to check to see if the child exists?
Yeah,
Is that what you meant?
like I was meaning like you no longer have to check to see like whether or not like the left and the right because that's part of the old logic. Like the new logic now
Yeah,
is just to
yeah.
like have the
Yeah, you don't need the old logic because to check if one is smaller than the max value
yeah,
means to check if it's smaller than five
right,
because
right.
max value was set to five, like in the previous iteration.
Okay, that makes sense. Yeah, yeah, and you don't need to check like whether or not the value doesn't exist because as soon as you call like validate on the other one, it'll just return true that it doesn't exist. Okay, that makes sense. Yeah.
Yeah. And then one last thing is this call isn't that's not necessary because
Oh,
if
because
root doesn't exist, yeah, it'll trigger validates
oh right, that makes
base
sense.
case.
Yeah, man, that's way more concise. What the heck? Okay.
Do you wanna I think the main thing is just like knowing that you can just let the recursion happen because the base case will catch it. Like you don't need to look ahead.
Yeah, that makes sense. Yeah. Huh.
Mhm.
And it's like oops, sorry. I'm just trying to the time complexity in this case, O of n. Space complexity would be okay. Space complexity for this one, it would be O of n also because you're storing everything in the call stack as you go along it, right?
Yeah, that's right. And it only finishes when the last call finishes.
Mm-hmm. Okay, so yeah, okay. I just it's always something like I thought was like kind of strange. You always include like the memory in the call stack as like part of like space complexity.
Yeah, yeah.
Yeah. Huh. So
I actually learned that like just after reading cracking the coding interview as well.
oh, actually, yeah.
Yeah. I actually didn't know how to do space complexity for like recursive functions until then.
Mm. You know, like this is a little bit of a tangent here, but I learned about like how important like the memory is on the call stack is from like my internship with EA. Like, yeah,
Oh, really?
yeah. I have to like you go through the call stack a lot. Like the IntelliJ is the goat for this. Like,
Oh, I see.
yeah. But like whenever I have to debug and like try to figure out what's going on, I always do that. But okay,
Mm.
let me do a quick run through and see. Hold up, wrong value? What the?
Hmm? What's the error? I don't see it. So
Oh shoot. Um, for case two one
can you
three,
describe it to me?
for case 213, it's returning false instead of true. I gotta think about that. Uh, huh.
I think you're in the trampoline, if you remember what that is. In the trampoline, line 65 in the code here, your float inf and float negative inf are flipped, I think.
Oh, okay. That's called the trampoline.
Yeah, because it's like it's you're launching the first instance.
Oh, okay. That makes
Yeah.
sense. Yeah. Is that an actual technical term for it?
Or well, that's what Gregor calls it in one like in 110.
Oh.
Does it work?
70 out of 83 test cases passed. The issue is with 222, like if they're all the same.
Oh, maybe it's not less than
Yeah.
or like greater than equals.
Yeah. I was thinking cuz like that's like what the description says. So yeah, it works.
I see.
It's accepted now. Okay.
Okay.
All right. That's hype.
Like the submission is accepted.
Yeah. Submission accepted.
Okay. Okay. And then I think the other piece of feedback that would be helpful is
Yeah.
like we lost a lot of time because we initially like didn't catch the correct answer, right?
Yeah.
Like we thought in the beginning that like in the beginning we ran with the idea of just checking your immediate left and right children.
Right.
And then you you ended up like coding up almost the whole solution before we switched to the correct high level thought, right?
Right. Yeah.
I think the problem there is like it's too expensive to go through and code up the solution that you think is true because
Mm-hmm.
if it's wrong, then you lost all that coding time, right?
Yeah.
So what's better is what'd be better is if you think of a high level solution, don't start coding it up. Write
Mm-hmm.
pseudocode or yeah, write pseudocode, explain it like in English in high level to the
Yeah.
interviewer, and then ask like, is this legit? And then they'll correct you. And that way you get to save all that time on coding.
That makes a lot more sense. Yeah.
Yeah. So like you in the beginning of the interview, I would just only discuss in high level
Mm-hmm.
and code once you have like literal confirmation from your interviewer
Mm-hmm.
that it's correct.
Yeah. Okay.
Or
That
if the interviewer like refuses to give confirmation, I guess you have no choice but to code
they
it
have to
up.
code
But
it
like
out. Yeah.
generally, like yeah, but generally like wait for
Oh,
confirmation.
also, just like another question: if you aren't able to come up with an optimal solution, do you think it's better to go like to just like code up a brute force one and like waste your time on that, or spend like the majority of the interview trying to think of like the optimal one?
Mm, I think if brute force doesn't take too long, I would just code it out.
Yeah.
Um, or honestly discuss it. Like just bring up the brute force to the interviewer, and
Yeah.
then if they say code it up, then code it up. If they say don't, then don't.
Oh, okay, that makes sense. Yeah.
Yeah, I'll just do what the interviewer like tells you to do.
Yeah. Oh, okay, okay, that makes sense. Yeah.
Yeah,
Oh.
and then I think the in the beginning I would I know like the question straight up just like gave you test cases,
Yeah.
but I would write out the assert statements, do like assert and then
Right. Right.
um yeah.
That makes sense. I gotta mimic your interview interview pattern more. It's so smooth.
Oh, thanks, man.
Yeah.
I stole it from a guy I coffee chatted.
Oh, actually.
What was it? Oh, Michael DeMarco. I stole it from him.
Oh, where do you oh, what is that? Where is he from? Like what
He,
company and
he's
stuff?
he, he's from UBC and he's like insanely goated. He worked at like Samsung, Tesla, like Google, stuff like that.
Bro, ultra sweat. What the heck? Yeah.
Yeah, Buddy is the goat.
Yeah. Okay. Well, okay, wait. Let me. All right, bye guys.